What happens when an interviewer wants to truly test your algorithmic efficiency? Merge case sorted lists is a pattern mastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity and pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns. Let's attack merge case sorted lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of k-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example: input 145, 134, 26. Output 1, 1, 2, 3, 4, 4, 5, 6. Real-world example: think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you on log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Now let's solve solution 1, merging k-sorted linked lists using a min heap. We'll see how to efficiently pick the smallest node among multiple lists using a heap. Step by step, we'll understand how the heap helps us maintain order. Time complexity is on log k, where n is the total number of nodes across all lists, and k is the number of lists. Each node is pushed and popped from the heap once, which takes log k per operation. The idea: use a min heap to always know which list has the smallest current node. Push the head of each list into the heap. Repeatedly pop the smallest node from the heap and attach it to the merged list. If the pop node has a next node, push it into the heap. Continue until the heap is empty. Think of it like picking the next smallest card from multiple decks. A heap helps you do it efficiently. Line-by-line explanation of the code. We import Python's heap key module to manage our min heap. This ensures the smallest value is always on top. We define the solution class to contain our merge function. This function takes lists, a list of k-sorted linked lists, and merges them into one sorted list. We create a dummy node to simplify building the merged list. The final merged list will start from dummy.next. Tail points to the last node in the merged list. We will keep moving it forward as we add nodes. Initialize an empty min heap. It will store tuples of node value, list index, to track the smallest node among all lists. Loop over each list's head. If the list is not empty, push its value and index into the heap, then move the list pointer to the next node. Loop until the heap is empty. Each iteration we extract the smallest node among the current nodes. Pop the smallest node from the heap. Val is the node's value. ID it tells us which list it came from. Attach the popped value to the merged list and move tail forward. If the list we just popped from has more nodes, push the next node into the heap and advance its pointer. This keeps the heap updated with the current smallest nodes. Return the merged list starting after the dummy node. And that's how this algorithm works. It first initializes a heap with the heads of all lists, then repeatedly picks the smallest node, adds it to the merged list, and updates the heap. Efficient, simple, and elegant. Heap operations cost O log k. For push and pop. Total nodes n overall complexity on log k. Space complexity is OK for the heap. Using a heap avoids repeatedly scanning all list heads to find the smallest node. Let's test our merge list function. We have 3 sorted lists: 1, 4, 5, 1, 3, 4, and 2, 6. The goal is to merge them into a single sorted list. We use a min heap to always pick the smallest node among the lists, adding nodes one by one to the merged list. The result is 1, 1, 2, 3, 4, 4, 5, 6, confirming the function works correctly. This approach efficiently merges multiple lists while keeping the order intact. This solution merges case-sorted linked lists using a divide and conquer strategy. Instead of merging lists one by one, it merges them in pairs repeatedly until only one list remains. This is faster and more efficient, especially for many lists. Time complexity is O(n) log k, where n is the total number of nodes across all lists and k is the number of lists. Each merge operation touches all nodes, but we reduce the number of lists by half each round, giving log k rounds. Define a class solution and the function merge lists. If the input list of lists is empty, return none immediately. Nothing to merge. Use a helper function merge2 to merge two sorted lists. Start with a dummy node to simplify handling the head, and a tail pointer to keep track of the end of the merged list. As long as both lists have nodes, compare their values. The smaller node is added to the merged list, and its pointer is moved forward. Tail always points to the last node in the merged list. After one list is exhausted, attach the remaining nodes of the other list. Return the merged list starting after the dummy node. Merge lists in pairs using an interval. Start with interval 1, merge list 0 with 1, 2 with 3, etc. After one round, double the interval to merge the merged lists together. Repeat until all lists are merged. Finally, return the fully merged list, which is now at index 0. Divide and conquer reduces the number of merge rounds, making it faster than sequential merging. Each node is processed once per merge, giving a total time complexity of O(n) log k. Space used is mostly for recursion stack in merge2, but the iterative implementation inside uses O(1) extra space. Let's test our function to merge multiple sorted linked lists. With 1, 4, 5, 1, 3, 4, and 2, 6, it merges two lists at a time until all lists combine into 1, 1, 2, 3, 4, 4, 5, 6. For empty input, it returns. This approach efficiently merges multiple lists, keeps order, and works reliably for any input. Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min-heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min-heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min-heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in O(n) log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min-heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists.